All right, let's take a look at triple integrals. Triple integrals, we've already seen a little bit of the idea. Here, generally, if we have three integrals, that means we're integrating in three directions, which generally is going to give us a volume. And generally, I believe this book uses Q. So this is just saying if we integrate over some volume, dV, then that is going to give us a volume. Now, in this case, in rectangular, dV is some combination of our differentials in each direction, like dy, dz, dx, so on and so forth. So if we don't have an argument with the triple integral, generally that's going to give us a volume. However, if we do have an argument here, and we have some, I don't know, some f of x, y, and z now could be in there, dv, what would this represent? Now we noticed each time we go up an integral, we add another dimension to what we're talking about. So one way to think about this isn't volume anymore, it would be like four-dimensional volume. Generally don't think about it like this, but another way that you can think about what this type of quantity could represent, if this was, say, a density function, right? Density times volume would give us mass. So if we knew the density of some solid and we integrated across the entire volume, it would tell us the entire mass of that volume. Now basically, with triple integrals, let's see if we can use triple integrals to set up volumes of different regions. So let's start with a very straightforward one. Let's say, find the volume created by, let's do something easy. How about 3x plus 4y minus 6z is equal to 12. In the first octave. All right, so again, we've drawn this picture several times by now because it's fairly easy to do. So to figure out where it crosses the x-axis, we let y and z be equal to 0, so that would be over here 4. Find out where it crosses the y-axis, we let x and z be 0, that would be over here 3. And for that, let's make that plus just to keep it in the first octave. For the z value, that would be here at 2. All right, so there we go. It's this triangular region again. So if I wanted to represent the volume of this using a triple integral, we have a few decisions to make. We got to figure out what order we want to do this in. dy, dz, dx, dz, dy, dx. You got several different combinations. The way that it works most of the time, and when we're in three-dimensional space, most of the time our functions, our surfaces, are functions of x's and y, basically z equals. So the most common way to do this is dz being first, since that's the most dependent variable most of the time. The next one would be dy most of the time, then dx. But we're going to do this at least one more way, just so you can see how the order of operation changes. All right, so when we're looking at this, what does z run from in this entire volume? Well, it runs from the xy plane, so down there on the bottom, that is z is equal to 0, over to the surface itself. So what does z equal on that surface? Well, solve for z. That would be 12 minus 3x minus 3y, or 4y, all over 6. Okay. So for this, z runs from z equals 0 to this. I'm just going to simplify that a little bit. That's going to be 2 minus 1/2 x minus 2/3 y. Okay, so z goes from z equals 0 up to that surface. Now that we've integrated the z's out, again, you want to kind of think about this as collapsing now. So we don't have any more z's. So what would that volume look like if it collapsed down just into the xy plane? In the xy plane, x goes out to 4, 1, 2, 3, 4. Y was at 3, 1, 2, 3. So that's what the region in the xy plane looks like after it falls down into there. So now we got to integrate across this region. Now, the way that I wrote it here was dy dx. So what does y run from? Y runs from everywhere in this region, from y equals 0 up to that. So we go from y equals 0 to y equals, well, that would be this line right here. So what is the equation for that line? Well, that would be where this surface crosses the xy plane. And in the xy plane, all the z's are equal to 0. So the equation just for the line, I'm just going to write it next to it, would be 3x plus 4y is equal to 12. So y would be equal to, if we solve for y, negative 3/4 x plus 3. Right, so just take this, solve for y. So everywhere in this region, y runs from 0 to negative 3/4 x plus 3. Okay, now that we've integrated out the y's, think about this as collapsing down just to the x-axis. So what does it look like on the x-axis? Well, it goes from 0 to 4. Again, you always want to check your bounds to make sure that you haven't broken any rules. Our first bounds are for z's. The only letters that can be in these bounds are x's and y's because those are the letters to the right. If you look at the bounds, the only letters we see are x's and y's. For the next integral, that's dy, the only letters that are allowed to be in these bounds would be any letters to the right of it, which would be x's. Notice we only have x's in those bounds. And then for the last integral, that's dx. Since we don't have any variables to the right of it, we can't have any variables in those bounds. Okay, so let's try this again. Let's set this up, and again, we're going to do a triple integral. I'm going to change the order for you. See if you can set this up as dy, dz, dx. So hit pause. The work's going to be quite a bit the same, but hit pause and see if you can come up with those bounds. All right, so if you're back, let me clean up our pictures here a little bit. This might help us. And see if we can come up with our bounds for this region. Now this time, I said we want to do y first. So what does y run from? So this is kind of left to right on the board here. Y goes from y equals 0, that's the back over there, that's y equals 0, over to the surface. Now on the surface again, we need to solve for y. So if we solve for y is going to be equal to 12 minus 3x minus 6z all over 4. So the y starts at the left side, goes from 0 to, and again I'm just going to clean that up, that's 3 minus 3/4 x minus 2/3 z, 3/2 z. And upside down, minus 3/2 z. Okay, so now that we have integrated out the y's, imagine all the y's collapsing so this thing only sits in the x, z plane. So now this collapses here to my xz plane. X was out here at 4, z was at 2. So there's the region, that little triangle region we need to integrate across. So in this case, this line right here is that line. So what is the equation of this red line over here? Well, since it's in the xz plane, we know all the y's are 0. So the equation for that would be 3x plus 6z is 12. Okay, so which way do we want to go first? In this, I told you to go z, so that would be vertically. So z always runs from here up to there in that entire region. So that is from z equals 0 to that line. So if we solve for z here, z is equal to negative 1/2 x plus 2. Okay, so z is going to run from 0 to negative 1/2 x plus 2. In our last direction, now that we've integrated all the z's, this collapses down to the x-axis from there to there. So again, x goes from 0 to 4. Okay, so there we go. There's what the region would look like if we set it up with a different order of operation. So if you want to not necessarily challenge yourself, but make sure you know what you're doing, try both of these integrals now and see if you end up with the exact same answer. It has to be because it's the exact same volume. All right, let's try a slightly more complicated shape. Let's see if I said find the volume between, let's say z is equal to x squared plus y squared and z is equal to 4. Now, it's not necessary that you sketch these regions, but you will find that you have much better luck if you do. So let's start out. Here's our 3D world. So our first surface, this is just our paraboloid. Looks something like that. And z equals 4 is a plane up here at, well, z equals 4. So really what we're talking about, it's kind of a bowl with a top on it. So what is the volume of that spot? So when we set this up, you have a choice of which way you want to set up your bounds. Let's just move it down here a little bit. Do you want to do dx, dy, dz, dz, dy, dx, all that? Well, here, since the main functions are defined in the z direction, I'm going to want to do z first. Now, you don't have to make all your choices at once. So what does z run from in this region? The bottom, if you think of bottom to the top, the bottom is always the paraboloid, and z is equal to x squared plus y squared. All the way up to the top is z equals 4. Right. Now, this is again where your imagination is really going to help you. Now, what does this region look like if you took this entire volume and collapsed all the z's out of it? Basically, if this just fell straight down to it, it didn't have any more z's, what would it look like? Well, that would collapse down to a circle in the xy plane. Now, what circle is that? Well, that would be this red circle here. I'm just going to kind of go around the outside of that. That red circle there would be what kind of collapses down in the xy plane. Well, that's where the paraboloid meets the plane. So that red circle would occur where x squared plus y squared is equal to 4. As you see, that intersection is a circle of radius 2. So what we'd end up with here, this would collapse down into the xy plane with a circle of radius 2. So that would be that equation. Okay, so since this is symmetric, it really doesn't matter whether or not we do dx dy or dy dx. I'll do dy dx here. What does y run from in this region? Well, it runs from the bottom of this circle up to the top of the circle, which means here I need to solve for y. Now, when you solve for y, hopefully you'll see you get plus or minus the square root of 4 minus x squared. Well, the bottom of this is y is equal to negative square root of 4 minus x squared, and the top is y is equal to the positive square root of 4 minus x squared. So in this region, it's going to be messy. Negative square root 4 minus x squared, positive square root 4 minus x squared. That's what y runs from. Now that we've taken out of the y's, think about this thing collapsing down just to the x-axis. What does x run from here? Well, it's going to run from negative 2 to positive 2. All right, so that's setting this up in our rectangular coordinate system. Now in this one, you can definitely see that polar would probably a pretty good idea because we got all these circle things laying around, but we haven't really talked about what polar looks like in 3 dimension. Well, we've talked about it, it's cylindrical, but we haven't done it with integrals yet. All right, so you need to make the first decision on what order that you want to integrate this in. If your functions are defined by a specific letter, like in this case z, you always want to do that first. Collapse it down into the plane that is the letters are remaining. So we use z, so we collapse it down in the xy plane, and then integrate across that 2-dimensional region.